So, what we learned so far, today we talk about the equipartition theorem, equipartition theorem. And if you find the time, we also will talk about the virial theorem. So, this is not the theorem, actually this comes from the equipartition theorem, but they call it theorem because we can prove that like a mathematical theorem. So, what we learned from so far, we learned from the phase space that, so if this is a typical phase space, I write it in the notation that you will understand that the horizontal axis denotes the number of the coordinate numbers, and the vertical axis show the momentum coordinates for the system. So this tree, as I explained that before, this is called degree of the freedom. So the total degree of freedom is 3, and so we call it F. F is the degree of freedom. It's actually the dimension for one particle's momentum or configuration vector, this Q, configuration vector. So, and the trajectory of the spatial surface, the surface that the Hamiltonian is constant, this kind of the system corresponded to the equilibrium state. Or some closed surface in the phase bottom. So this is very important to mention here that the translation of equilibrium in statistical physics is translated to the hypersurface given by this equation H equal to E, and E is a constant. So as long as you have this kind of the surface in your space when the Hamiltonian is equal to E, so you can be sure that you are living, or your system is stay in the equilibrium state. Each one is corresponding to one of them, so H minus EI is 0. So this is the equation for any of this surface. But surface, so this is a boundary actually. Huh? From now I want to mention here that this constraint, this is called as constraint. This constraint, by this constraint you can make a set of the closed curve in the phase pole where we call it this first integral, or we call it that the equal energy, or say equal energy surface. So this is the equal energy surface, we can call it. And they are on the boundary. But in a statistical physics, you know that we are looking for this. Still, I am continue to say that we are looking for the omega MVE, and for microcanonical systems, this is only a function of the E, and this is actually proportional to the volume of phase space, not the whole phase space. The duration of the phase space, which is given in the band of the energy like that, proportional actually to that. So you need a proportionality constant. So we explained that before, that it will be proportional to 1 over h dq dp dtn. You can write 3n here over this. You can write a prime here, or you never mind. So it means that the integration should be taken over this surface, over the volume, not surface, over the volume which is given by this equation. So this is the volume, or this is the range of integration. And this is we can write this omega 0 as the unit volume of the phase space. Huh? You remember how it came from the principle of Heisenberg, delta P delta Q is over the log H or H bar. So basically by different way you can show that this is a omega. And you will learn a technique that to calculate this integral you don't need to have a two hypersurface. So you can use the Taylor series, so you can write delta over epsilon partial derivative of this, the normal integration when you have just the Hamiltonian bounded in this range, d3 and a q, d3 and a pair. Or very generally you can write even dq, dp, and then do not mention the dimension of the space. So this is the old one. Actually, I teach that before. So now I want, this is for microcanonical. For canonical, next chapter we will talk about the canonical. So I want now prove a theorem called equipartition theorem. Equipartition theorem is equipartition. It's about the expectation value or average first moment of the gradient of the Hamiltonian. This is the title which I find that is more in phase space. This title reflected the idea of partition function more than the other statement. I will translate this to the equation. You will see that. First it's the average. So you will have the average. So this is the average. Average of the first moment or second momentum or first momentum. You know that it's integral x. The f of x is the first moment of the in classical mechanics. And if you have the second momentum, so you have a x squared f x. The v, if you have a high volume. So this is the first momentum. So it should have something like that. The gradient of the Hamiltonian in phase space, partial derivative of h with respect to the x. So what is the x? You are living in the phases progress. So this x could be any of the coordinate q or p. So it's a general coordinate. So I can call it I, and here I want to make it that those difference xi and xj. So the xi can be any of them. 6 and coordinate. Any of them can be seated here as a xi, and the xj can be other one. I want to mention here that it doesn't mean that these two coordinates are the same. For example, if this is a momentum, it can be coordinated q. If this is a q, it can be p. So it can be also pp, can be q, q, q. So this is a generally. We will prove that surprisingly this is equal to the kT delta H. T is the temperature, so it's the only parameter for microcanonical system. Temperature. So the average of the first momentum of the gradient of Hamiltonian is given by. So you are a physics student, so you need to know the proof. You need to know that. That's our difference actually with the engineering. So I was trying to find a more beautiful proof for this theorem, but so far we need just to stick to the old proof. So the proof is very short actually. It's not very strong proof actually. This is for any ensemble, so it can be for any ensemble you can do that. For microcanonical and for canonical you can do that. I mean, your thermodynamical system, a statistical system should be fixed in one of these two ensembles, you know, microcanonical or canonical, either canonical or microcanonical.
Is this symbol for Dirac delta function or
no, this is a Kronecker delta. Yeah, this is a Kronecker delta. So Kronecker delta is just a 2 symbol x index, just for avoiding writing that 1 0 1 0. Delta Dirac is not function actually. Delta Dirac is a distribution, and this is a continuous distribution of the one parameter. Anyway, we will use delta Dirac, but not now. So this is the Kronecker symbol. So the proof is that what's the expectation value of anything in the phase portrait is just multiply the function to the density function over the volume dq dp This is a general, not for microcanonical, for any ensemble. Canonical and grand canonical also microcanonical. Just multiply the function which you want to find the average in the density of the probability, the statistical probability, and divide that to the total probability or total value. But these integrations are over. I want to do that for the microcanonical because it's more easy. For microcanonical, you have this bond. For microcanonical, we explained that microcanonical is the easiest form for the ensemble. So rho is a unit constant. Yeah, and so I can Q dq dp over dq. That's all. So again, I can do one more thing, is that this is the unit volume of the phase space if Hamiltonian was between 0 to E. Anyway, this is the unit volume. This is a unit volume, is a constant, is some power of the h. Is some power of h, so even you don't need, here you needed to write the prime, means that integration should done in this bond of the Hamiltonian, but here I can remove that because there is no any function to be worried about that, even if you can keep it. Anyway, it's up to you. For me, it's important the first one. So the first one will be translated to this Taylor series actually. P, dq, dp. There are different, you can write it as D3N, D3QP. If you are 3-dimension actually, sometimes you can write it that also d omega, how you want. So the notation is just, sometimes they write dvqp. So anyway, any of them. But I use dq, dp just for simplicity. But you needed that to be very careful about this integral because this integral is very tricky. You needed to take the partial derivative of these integrals, yes, with respect to the e, but the problem is that the e appears as the limit for the integral. Integral is from 0 to e. Yeah, this is the. So we need to develop a technique to take the derivative from the integral, which when the boundary of the integral are moving. can remove that because we will back to this. Okay, this is for general f, for any f you have. I want to explicitly do this calculation for xi pj. So will be delta omega 0 partial derivative of the En integral from 0 to En. The Hamilton in the Q and the pair should be constant between 0 to E. This is just symbolic because the limit will be some Q to some pair and some P to some other P. P1 to P2, but I write just because I want to mention that even if you have anything here, it will be function of the E. So this is the correct limit actually. From here you need to understand that what is the range of the Q and the P. And it depends to your surface. For example, is a circle, is a ellipse, or any other things. So you have here xi, partial derivative of this with respect to xj, dA, Q, dA, okay? Okay. Only okay, so I wanted to take the derivative of that with respect to the E, but I need to be very careful from this. Before, can I write this integral like that? Partial derivative of E, respect to 0 to E. Okay, I want to write that. Yes? Do you know what I did at here? I used the derivative. I write this as a complete derivative. If you expand this, will be the first derivative multiplied to that minus the second derivative. So this will become nothing new here.
Dr. dx by dn?
dxi, partial xi, partial xj. What does it mean, partial xi, partial xj? For example, look at that, what will be. So if both of them are q, so it will be partial derivative qi, qj. So you know that, so it looks like that, partial x, partial y. So x and y are independent coordinates, so that will be 0, or partial x will be 1. So in case, it will be either 0 or 1. Now I do something else. Consider the second coordinate like p, for example. If I write that, it looks like partial derivative x, partial derivative x. Momentum and the coordinate are independent from each other in the phase portrait, so I can write it as 0, 1, 2. And the other possibility is pi, j, so this is exactly like the same case. I write, for example, one that pi y is 0 and pi x is 1. So I can write that delta ij. This is a delta ij. So minus delta omega delta ij partial derivative dot E, integral is 0 to E, h dq dp. Yes? Just plus delta omega 0, partial derivative of the E. Nothing, I just use this fact. Okay. So far there is nothing here complicated. This is a difficult, so I will keep it that later. This is a difficult one because partial derivative with respect to the E, and E is appear here, Hamilton is appear here, Hamilton is between 0 to E. So this is the hard part. But this is not very hard. I can use the Gauss theorem or divergence theorem. You know that divergence of any vector field in the volume